Hello everyone and welcome to Control Engineering Tutorials. In this tutorial, I will explain one very important technique for designing feedback control systems. Namely, I will explain how to place or assign poles of the closed-loop system such that we meet the requirements on desired overshoot and rise time of the transient response. That is, we want to design a feedback controller that shapes the transient response. And this is one of the main problems in control engineering. So let us immediately jump on the problem. So here is our problem. Let us consider the following open loop transfer function. We need to design a state feedback control system such that the following requirements are satisfied. The rise time should not be larger than 1 second and the overshoot should not be larger than 10%. Let us illustrate these desired specifications graphically. The x-axis is the time axis and we denote time by t. The y-axis is the output of the system and we denote the y-axis by y. A typical transient response of the system looks like this. This is a steady state value, and we will denote this steady state value by YSS, where SS stands for steady state. First, let us explain the overshoot. This dashed line is the steady state value, YSS. The maximal peak is usually denoted by M. The overshoot is usually defined as M over YSS multiplied by 100%. Our first design specification is to keep this overshoot below 10%. Let us explain the rise time. Basically, the rise time is defined as follows. It is the time it takes for the transient response to reach from 10% to 90% of the steady state value. So the rise time is the time that it takes for the transient response to go from 10% to 90% of the steady state value. And this is the time, TR, where R stands for rise time. The rise time should be less than or equal to 1 second. This is the second design specification. Before I explain how to solve this problem, I will stop here for a second and mention two important things. First of all, those of you who are my subscribers or who follow my work know by now that I always create a post that nicely summarizes everything that I will explain in this video, and consequently here is the post. This post contains all the explanations, equations, figures, and even MATLAB code that you can find over here at the end of this post. Secondly, it took me a significant amount of time, energy, and planning to create this video and this post, and I consequently ask you to press the like and subscribe buttons. Thank you very much. Okay, so let's see how to solve this problem. The first step is to develop a state space model corresponding to our original system. To develop this state space model, I will use the controllable canonical form, and I explained the controllable canonical form in one of my previous tutorials. You can find this tutorial by clicking over here and by following this link. And here is the tutorial. I strongly suggest you to go over this tutorial in order to better understand the material presented in this video. We use this approach since the controllable canonical form enables us to quickly compute the characteristic polynomial of the closed-loop system. And of course, we can also use other methods for pole placement, such as MATLAB's function place or Ackermann's formula, for example. The first step in deriving the controllable canonical form state space model is to multiply the terms in the denominator of our transfer function. So I multiply s squared with this term over here, and I obtain this polynomial over here. The polynomial in the numerator is usually denoted by b of s, and it's equal to 1, and the polynomial in the denominator is equal to s to the power of 3 plus 4s squared, and I will write this polynomial in its general form, s to the power 3 plus general coefficient a1 multiplying s to the power 2 plus a2s and plus a3. And similarly, I will write the general form of the polynomial in the numerator of our transfer function. B of s is equal to b1 multiplying s to the power 2 plus b2 multiplying s plus b3. The general form of the controllable canonical form is the following. X dot is equal to minus a1 minus a2 minus a3 1 0 0 0 1 0 multiplying the state plus 1 0 0 multiplying the input, and the output equation is simply y is equal to b1, b2, b3, and this is our C matrix multiplying x. Now, by substituting these coefficients from these particular forms of the polynomials, we can obtain this state space model. And this is exactly the state space model in the controllable canonical form. Our goal is to design a feedback control law in this form such that the poles of the closed-loop system are placed at proper locations that we need to determine in the sequel. So let us analyze this control law. Basically, this is a standard feedback control law where k is a row vector and x is the state. And minus sign comes from the fact that we have a negative feedback. Later on, I will modify this law to include a reference signal such that we can track a step control input. To determine the pole locations, we need to somehow parameterize the system poles. Usually, the system poles are parameterized by using the damping ratio zeta and the natural undamped frequency omega n. This figure over here shows this parameterization. We basically have complex conjugate poles. This is the first pole, and this is the second one. Omega n is simply the distance from the origin in the complex plane to our pole. Zeta is the cosinus of this angle, theta. Obviously, if cosinus of this angle is equal to 1, that is, if theta is equal to 0, we have a perfectly damped system, that is, both poles are over here. So we can parameterize the poles as follows. This is the real part, it's equal to zeta times omega n, or omega n times cosinus of this angle, That is, this is the real part, and it's exactly zeta times omega n, and imaginary part is equal to omega n times sinus of theta, and sinus of theta can be expressed as square root 1 minus cosinus square of theta, and cosinus of theta is equal to zeta. So we have 1 minus zeta square under the square root. And these are our complex poles that are parameterized in terms of zeta and omega n. Now, here's the main idea of our solution. On the basis of desired transient response specification, that is, on the basis of the desired value of the overshoot and the transient response, we can find zeta and omega n. Now, our original system is of the third order. So we have in the numerator s squared multiplying s plus 4. However, to design zeta and omega n, we will for just a second assume that the system is of the second order and that it can be represented by this prototype over here. That is, the equation number 7 represents a generic form of the second order system. And you can see how this transfer function is parameterized in terms of zeta and omega n. Now, this approach approximates the dynamics of the dominant poles fairly well, as long as the third pole is placed far away from these dominant poles. So our main idea will be to use this second order approximation to place the complex conjugate poles somewhere over here, and these locations will be determined on the basis of the desired transient response of the system, and the third pole will be placed relatively far away from these two dominant poles. In this way, we can tackle this problem. For the generic transfer function given by the equation 7, we can relate the overshoot and rise time with the damping ratio zeta and natural undamped frequency omega n. We can use the formulas given in the chapter 7 of this famous book, Automatic Control Systems by Benjamin Kuo. The formula for the overshoot is given over here. We can see that the overshoot only depends on zeta. On the other hand, the rise time is given by this formula. We can see that the rise time depends on zeta and omega n, and we can see that the rise time is inversely proportional to omega n. From the equation number 8, we can express the damping ratio zeta, and as the result, we obtain the equation number 10. Now, in this equation, we can directly substitute the value of the maximum overshoot. So if we substitute here 10%, we obtain this value of zeta. Now, I want to round this value of zeta. So how to round it? It's a good idea to round it to a larger number, since larger zeta gives a more stable system, that is, increases damping. So by rounding this number to 0.6, I obtain the final value of zeta. On the other hand, from the equation number 9, we can express omega n. And by expressing the omega n parameter, we obtain the equation number 13. We substitute zeta from the equation number 12, and we substitute the desired rise time of 1 second, and as the result, we obtain omega n of 1.7731. Again, it's always a good idea to round these numbers, so since larger values of omega n produce smaller rise time, we round this number to obtain the final value of omega n, and the final value of omega n is 1.8. Now, by substituting these values of omega n and the value of zeta given over here in our general parameterization of the system given by these equations, we can obtain the closed loop poles that approximately guarantee the transient response. That is, that guarantee the desired values of rise time and overshoot. And these are the poles. We place the third pole relatively far away from these poles. We choose a real third pole in order to specify and to simplify our design. The desired closed-loop characteristic polynomial has the following form, given by the equation 18. So we simply substitute the computed poles in the general form of the characteristic polynomials. We substitute S1, S2, and S3, and after multiplying the terms, we obtain this polynomial. And this is our target polynomial. Now we want to design a feedback control algorithm, that is, we want to design the entries of the matrix K, that is K1, K2, and K3, such that the characteristic polynomial has this form. By substituting the feedback control algorithm in our state equation, we obtained the closed loop state equation. So let us see and let us analyze this matrix. Let us perform basic matrix multiplication. So this is my original matrix A, this is B vector, this is the parameterized version of the matrix K, and as the result I obtained the closed loop matrix A minus BK that looks like this. And let us analyze this matrix. The first thing that you need to observe, and the most important thing that you need to observe, is that this matrix is in the controllable canonical form. And this is a very important observation. This means that we can directly construct the characteristic polynomial on the basis of this matrix. And the characteristic polynomial FCL is the following. It's the third order system, and you can see immediately that the first coefficient multiplying s squared is this term over here. So it's 4 plus k1 times s squared. So it's minus this coefficient over here. Similarly, the second coefficient is minus k2, and that's k2s, and the third coefficient is minus k3, and that's simply k3. And this is our characteristic polynomial that's being parameterized by the coefficients of the feedback control matrix. And we are almost done. This target characteristic polynomial, that is equation 18, should be equal to the equation number 21. And by setting the right-hand sides of these two equations to be equal to each other, we obtain this equation over here. Now, two polynomials are equal if their coefficients are equal. And from this equation, we obtain three additional equations that need to be satisfied. So 4 plus k1, that is this term, should be equal to this term over here, that is this coefficient. k2 should be equal to this coefficient, and k3 should be equal to this coefficient. And we obtain a system with three unknowns, k1, k2, and k3, and we have three equations. Consequently, we can solve this system, and the solution is given over here. K1 is 4.0963, K2 is 15.72115, and K3 is 18.8623. and these coefficients uniquely determine the feedback control matrix. And we are almost done, except for one very important detail. Notice over here that we designed a closed loop system that looks like this. However, what will happen with the state over here? Since this matrix is Hurwitz, when I say a matrix is Hurwitz, this is just a fancy term for saying that this matrix is stable. However, I cannot even say that the matrix is stable. I can only say that its eigenvalues are strictly in the left half of the complex plane. So, and you immediately see a problem over here. Since the system is stable, all of my states will go to zero after some time. However, you want to design a closed-loop system such that you follow a certain trajectory or a certain input. So we need to add here a term, and not only a term, we also need to define its matrix such that we follow a reference trajectory. And let us see how to perform this important and final step. To add the reference signal, we perform the following analysis. So let us consider our original system. And let us assume that there exists a constant input that produces a steady state output and steady state excess. Then input, output, and the steady state need to satisfy these two equations. Basically, if we have a steady state and the steady state is constant, then its derivative is equal to zero, and consequently we have a zero over here. By subtracting these two equations, we obtain this state space model. So I simply take the state equation, this state equation, and then I subtract from this equation, and I obtain this equation over here. And then I define a new state, x tilde, that's equal to x minus x steady state, and u tilde, that's equal to u minus us. And you can clearly see that since xs is a steady state, x tilde dot is equal to x dot, and by using this fact, we can transform the equation 27 and we can obtain the equation 29. This equation 29 is usually called the equation in error state space, since x tilde can be interpreted as some form of error. The same holds true for the input u tilde. Now, it's very important to observe the following. Since A and B are exactly the same and exactly identical to A and B matrices of our original system, we can see that a feedback control law having this form over here, I'm only missing here a minus sign, and I will correct this in the post, is identical to the control law of our original system. That is, if we design a feedback control law for our original system that looks like this, the K will be the same as the K that stabilizes the system given by the equation 29. That is, the closed loop poles of this system will be identical to the closed loop poles of this system for the same matrix K. And this is a very important fact to keep in mind. By expanding this equation, that is the equation number 30, we can obtain this equation. And to see that, you can simply write u tilde is equal to u minus us, and that's basically equal to minus k multiplying x minus xs. And if you multiply the terms and if you transform this equation, you will obtain the equation that you can see over here. The next step is to parameterize us and xs. And I will introduce my reference signal. The reference signal is the input to your control system, because keep in mind that the typical control system looks like this. We have a reference signal, we have a controller, we have a plant, and this is our output, and this output is fed to the summation block over here. So this is our reference signal, and this is the input to the control system. So we can simply parameterize US and R in terms of R, where KU and KX are two new matrices that we need to find. And we will find these matrices such that our system accurately follows step reference signals. So let's see how to do that. Now, since R is a constant signal, we can substitute these two expressions in our transformed system. So what happens over here? Remember that the transformed system looks like this. Now, look what happens here. We want that the output of system becomes R. That is, we want our output to be equal to the reference signal in the steady state. So simply YS becomes R. On the other hand, we substitute US and XS by using these two terms. The next thing to observe in this equation is that we can simply cancel R and we can erase R from both sides. And as the result, we obtain the equation given by the equation 34. We can write this equation in the matrix form to obtain this equation over here, where Kx and Ku are the matrices or scalars that we need to determine. Obviously, if ABC0 matrix is invertible, the solution will be given by the equation 36. Under the assumption that we have computed Kx and Ku from this equation, we can substitute these two equations. That is, we can substitute Ku and Kx in the control law given by the equation 31. That is, we can substitute these terms in this equation, and as the result, we will obtain this control law. And this is the final form of the control law. So U becomes minus Kx, and remember that we defined Kx by properly placing the poles of the closed loop system such that the transient response specifications are met, and we have this term over here that enables us to track a step signal in the steady state response. And BR matrix is given over here. And the final form of our system is given by the equation 38. All these calculations can be performed in MATLAB. And here's the MATLAB code I wrote. Basically, we define the desired overshoot. Then I compute zeta by using the formula I explained previously. Then I define my desired rise time. Then I compute omega n. Over here, I place the poles. I define my closed loop system. I compute the matrices Kx and Ku by inverting the matrix. That is, by inverting this matrix, and this matrix is called matrix 1. And then I define my feedback control matrix. I define my closed loop matrix. I check the eigenvalues. I define my B matrix like this. And finally, I simulate the step response of the system given by the equation 38. And the step response is given over here. And this is the final graph of this presentation and this tutorial. We can clearly see that basically the rise time is properly met in practice. That is, the desired rise time is approximately 1.1 second, right? That still can be a little bit improved. However, this is still relatively good since we are using very crude approximations. And finally, you can see that the overshoot is around 9%, and that's less than 10%. And finally, the closed loop control system looks like this, and we can clearly see that in steady state we can accurately follow the step signal. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much and have a nice day.